What's up, buddies and buddy girls? Today we are going to continue reading the book Welcome to the Universe. And we are now on chapter 2. It's called From the Day and Night Sky to Planetary Orbits. This chapter is also written by Neil deGrasse Tyson. In this chapter, we will cover 3,000 years of astronomy. Everything that happened from antiquity, the time of the Babylonians, up until the 1600s. This is not going to be a history lesson, because I'm not going to cover all the details of who thought and who discovered what first. I just want to give you a sense of what was learned during all that time. It begins with people's attempts to understand the night sky. Let's draw Earth next to the sun. It's not drawn to scale in either size or distance. Here's the sun. So I guess there's a figure of the sun. Let's draw Earth next to it. It's not drawn to scale in either size or distance, but is simply meant to illustrate certain features of the Sun-Earth system. Way out, of course, are the stars in the sky. I'm going to pretend that the sky is just stars, dots of light on the inside of a big sphere, which will make some other things easier to describe. Earth, as you probably know, spins on an axis, and that axis is tilted relative to our orbit around the sun. That angle of tilt is 23.5 degrees. How long does it take for us to spin once? A day. How long to go around the sun once? A year. 30% of the general public in America who were asked that second question got the wrong answer. A spinning object in space is actually quite stable, so that as it orbits, its orientation in space remains constant. If we move the Earth around the sun from June 21st to December 21st, as it comes around the other side of the sun, to the right in figure 2.1, okay, there's another figure, Earth will still preserve that spin orientation in space. Its axis points in that same direction for the entire journey around the sun. This makes for some interesting features. For example, on June 21st, a vertical line perpendicular to the plane of the Earth's orbit divides the Earth into day and night. What can you say about the part of the Earth to the left of that line, away from the sun? That's nighttime. But on December 21st, when Earth is on the opposite side of its orbit, nighttime is now the opposite side, to the right in the illustration. Sorry, I can't really show you these. All the people on Earth who look up in the nighttime can see only that part of the sky opposite the sun. The nighttime sky on June 21st is different. The stars on the far left from the nighttime sky you see on December 21st. The stars on the far right. During the summer nights, we see the summer constellations, such as the Northern Cross and Lyra, whereas during the winter nights, we see the winter constellations, such as Orion and Taurus. Figure 2.1. Earth circles the sun, providing different nighttime views as the seasons change. Because of the tilt of the Earth's axis relative to its orbit on June 21st, the northern hemisphere receives the sun's rays more directly, while Australia and the entire southern hemisphere receive them obliquely. On December 21st, people south of the Antarctic Circle see daylight for 24 hours as they circle around the South Pole as Earth rotates. So that's basically explaining the illustration that I can't show you. Let's look at something else. On December 21st, if it's nighttime, to the right of the vertical line, and Earth turns on its axis, what about the upside down people standing in Antarctica, south of the Antarctic Circle? They go around the South Pole. Does a person there see darkness? Nope. On December 21st, a person there sees 24 hours without dark, 24 hours of sunlight, as Earth rotates. There is no nighttime for anybody within the entire south polar cap of Earth on that day. That's true for anyone between the Antarctic Circle and the South Pole. Following this argument, if I come up to the North Pole and I watch people north of the Arctic Circle revolve around the North Pole, Santa Claus and his friends, they never rotate into the daytime side of Earth. For them, on December 21st, there are 24 hours of darkness, as you might suspect. On June 21st, the reverse happens. It's the people of the south of the Antarctic Circle who have no day at this time of the year, and the people in the Arctic who have no night. Let's observe from Princeton, New Jersey. It's close to New York City, but with no skyscrapers or bright city lights to interfere with the view. The town's latitude on Earth is about 40 degrees north. At dawn, on June 21st, the northern hemisphere rotates New Jersey into daytime, receiving quite direct sunlight, whereas the sunlight hitting the southern hemisphere is rather oblique to Earth's surface. Noon is when the sun reaches its highest point in the sky. Did you know that nowhere in continental United States is the sun ever directly overhead at any time of day, on any day of the year? Odd, because if you grab people in the street and ask, "Where's the sun at 12 noon?" most will answer, "It's directly overhead." In this case, and in many others, people simply repeat the stuff they think is true, revealing that they've never looked, they've never noticed, they've never conducted the experiment. The world is full of stuff like that. For example, what do we say happens to the length of daylight in the winter? The days get shorter in the winter and longer in the summer. Let's think about that. What's the shortest day of the year? December 21st, which is the solstice, and also the first day of winter in the northern hemisphere. If the first day of winter is the shortest day of the year, what must be true for every other day of winter? They must get longer. So days get longer in the winter, not shorter. You don't need a PhD or a grant from the National Science Foundation to figure that out. Hours of daylight get longer during the winter and shorter during the summer. What's the brightest star in the nighttime sky? People say the North Star. Have you ever looked? Most haven't. The North Star, also known as Polaris, is not in the top 10. It's not in the top 20. It's not in the top 30. It's not even in the top 40. Australia sits too far to the south for anybody there to see the North Star. They don't even have a South Pole star to look at. And while we're talking celestial hemispheres, don't ever be jealous of the constellations in the southern sky. Take the Southern Cross. You may have heard about it. People write songs about it. But did you know that the Southern Cross is the smallest constellation out of all 88 of them? A fist at arm's length covers the entire constellation completely. Meanwhile, the 4 brightest stars of the Southern Cross make a crooked box. There is no star in the middle to indicate the center of the cross. It's more accurately thought of as the southern rhombus. In contrast, the Northern Cross covers about 10 times the area in the sky and has 6 prominent stars. It looks like a cross, with 1 star in the middle. In the north, we've got some great constellations. The North Star is actually the 45th brightest star in the nighttime sky. So do me a favor and grab people in the street and ask them that question, and then set them straight. If you must know the brightest star in the nighttime sky, it's Sirius, the dog star. Now, let's compare what happens to the sunlight at 2 locations on Earth. Look at the ground at noon in Princeton. On June 21st, sunlight hits from a very high angle. The 2 parallel rays traveling from the sun hit Princeton only a short distance apart on the ground. The ground at Sydney, Australia, at noon takes in a similar pair of rays, except that the rays are coming in at a much lower angle and are spread much farther apart on the ground. What's going on here? Which place is getting its ground heated more efficiently? Princeton, of course. The energy impinging on Princeton's ground is more concentrated because of how directly the rays intersect Earth's surface, making Princeton's ground hotter. It's summertime in Princeton on June 21st. At this time of year, it's winter in Sydney. The reverse will apply 6 months later on December 21st. The sun heats the ground heats the air. The sun does not appreciably heat the air itself, which is transparent to most of the energy that comes from the sun. The sun's energy peaks in the visible part of the spectrum, and you already know that you can see the sun through the atmosphere. From this we conclude the obvious fact that the sun's visible light is not being absorbed by the air. Otherwise you wouldn't see the sun at all. If you are indoors in a room with no windows, you can't see the sun because the roof of your building is absorbing the visible light from the sun. You must either look out a transparent window or go outside to see the sun. So in sequence, light from the sun passes through the transparent air and hits the ground. The ground absorbs the light from the sun and then re-radiates that energy as invisible infrared light, which the atmosphere can and does absorb. We'll talk more about these other parts of the spectrum in Chapter 4. The ground absorbs visible light from the sun, gets hotter, and then the ground heats the air through the infrared energy it emits. This doesn't happen instantaneously. It takes time. But how much time? What's the hottest time of day? It's not 12 noon, the time of peak ground heating. The hottest time of day is never 12 noon. It's always a few hours later because of this effect. 2 p.m., 3 p.m., even as late as 4 p.m. in some places. So that's summertime in the northern hemisphere. In summer, the north pole of Earth's axis tilts toward the sun, and of course this is winter for those in the southern hemisphere, for the same reason that the hottest time of day is after 12 noon. The hottest time of year in the northern hemisphere is after June 21st. That's why the season of summer starts on June 21st. And it gets hotter after that. Similarly, December 21st is the start of winter in the northern hemisphere, and it gets colder after that. 3 months later, on March 21st, spring starts. Every part of Earth rotates both into sunlight and out of sunlight on the first day of northern hemisphere spring. And on the first day of northern hemisphere fall, September 21st. So everybody on Earth gets equal amounts of darkness and lightness on those 2 days, the equinoxes. Earth's north pole points toward Polaris, the North Star. A cosmic coincidence? Not really, because we don't point exactly there. You can fit 1.3 full moon widths between the actual spot in the sky where our axis points, the North Celestial Pole, and the position of Polaris. Let's go back to Princeton, as shown in figure 2.2. Another figure, sorry. Standing there at night, you'll see any star on one side of the sky. At that instant, in the figure, these stars are marked stars visible above Princeton's horizon. Princeton's horizon is drawn, this line is tangent to the surface of Earth where you're standing. When you look up, you'll see stars making circles around Polaris as Earth turns. So there's a cap in the sky where these stars make circles around Polaris, but never actually set below your horizon. These are called circumpolar stars. Suppose you look at a star farther away from Polaris. That star sets, then comes around and rises again. That's what the sky looks like, the view from Earth. One of the more familiar asterisms, star patterns, of the night sky is the Big Dipper, well known because its stars are bright and it goes around Polaris. It dips down, just skimming the horizon, as seen from Princeton, and then comes back up again. Anything much farther from Polaris than the Big Dipper actually sets. How high is Polaris in angle, as seen from Princeton? We can figure this out. First, let's say we have gone to visit Santa Claus at the North Pole. Where's Polaris in the sky? If you're visiting Santa Claus, Polaris will be almost directly straight overhead. It's always straight overhead there. A star halfway up in the sky, as seen from the North Pole, circles Polaris as Earth turns, always staying above the horizon. A star right on the horizon circles along the horizon. So every star you can see stays above the horizon. No star rises, no star sets. They all circle Polaris overhead, and you see the entire northern hemisphere of the sky. That's Santa's view. What's the latitude of the North Pole? 90 degrees. What's the altitude of Polaris from the horizon, as seen from the North Pole? It's 90 degrees, the same number. That's not a coincidence. Polaris is 90 degrees up, and you're at 90 degrees latitude. Let's go down to the equator. What's the latitude of the equator? 0 degrees. Polaris is now on the horizon, 0 degrees up. That's my latitude. Or what's my latitude in Princeton? 40 degrees. So from Princeton, the altitude of Polaris is 40 degrees above the horizon. People who navigate by the stars know that the altitude of Polaris you observe is equal to your latitude on Earth. Christopher Columbus set sail at a fixed latitude that he maintained for his entire journey across the Atlantic Ocean. Go back and look at his maps. That's how they navigated. They kept at that altitude by keeping Polaris at the same altitude above the horizon during the trip. Did you ever play with a top when you were a kid and watch the top wobble? Earth wobbles. We are a spinning top. Under the influence of the gravitational tug from the sun and moon, we wobble. The time it takes to make one complete wobble is 26,000 years. We rotate once in a day and wobble once in 26,000 years. That has an interesting consequence. First, consider the sphere of the stars that I drew around the solar system. As Earth moves around the sun occupies a different place against the background of the stars. On June 21st, the sun sits between us and the stars on the far right, which means that the sun passes in front of those stars as seen by us on June 21st. But on December 21st, the sun is between us and the stars to the far left. In between times, the sun occupies a place in front of different sets of stars throughout the year as it circles the sky. Long ago, when most of the world was illiterate, when there was no evening television, no books or internet, people put their culture onto the sky, things that mattered in their lives. The human mind is very good at making patterns where none really exist. You can easily pick patterns out of random assortments of dots. Your brain says, I see a pattern. You can try this experiment. If you're good at programming a computer, take dots and place them randomly on a page. Take about 1,000 dots. Look at them, and you may think, hey, I see Abraham Lincoln. You'll see stuff in a similar way. These ancient people put their culture on the sky when they had no other idea what was going on. They didn't know what the planets were doing. They didn't understand laws of physics. They said, the sky is bigger than I am. It must influence my behavior. So they supposed. There's a crustacean-looking constellation of stars over here, and it's got some personality traits. The sun was in that part of the sky when you were born. That must have something to do with why you're so weird. And then over here we've got some fishes, and over there we've got some twins. Because we don't have HBO, let's weave our own storylines and pass these stories from person to person. In so doing, ancient peoples laid out the zodiac, the constellations, in front of which the sun appears to move throughout the year. There were 12 of these zodiac constellations. You know them all. Libra, Scorpio, Aries, and so on. And you know them because they're in nearly every daily news feed. Some person you've never met makes money telling you about your love life. Let's try to understand that. First of all, it's not really 12 constellations that the sun moves through. It's 13. They don't tell you that because they couldn't make money off of you if they did. Do you know what the 13th constellation of the zodiac is? Ophiuchus. I know you know what your sign is, so don't lie and say, I never read my horoscope. Most Scorpios are actually Ophiuchans. Let's keep this up for a minute. When did they lay out the zodiac? It was encoded 2,000 years ago. Claudius Ptolemy published maps of it. 2,000 years is 1/13 of 26,000 years, and almost 1/12. Do you realize that because of Earth's wobble, we call it Precession, the official term? The month of the year in which the sun is seen against a particular constellation in the zodiac shifts. Every single constellation that has been assigned to the dates identified in the newspapers is off by an entire month. So Scorpios and Ophiuchans are currently Librans. Therein lies the greatest value of education. You gain an independent knowledge of how the universe works. If you don't know enough to evaluate whether or not others know what they're talking about, there goes your money. I think I'm going to end it right there and continue on with this chapter next week maybe. I hope you guys enjoyed this, and I will see you again soon. Come back on Friday and check out the new Facts Friday for the week. It's going to be an old style facts video, meaning fact 1, fact 2, fact 3, fact 4. And that's all. Have a great rest of the week, and I'm having trouble with my words today. Yeah. Thank you for watching. I'll see you again soon.